Suppose you have categorical data. What can you do with this type of data? What we do is create what we call a success category, which defines some characteristic in which we're interested. We then find the proportion or ratio of values that have this characteristic, either for a sample or an entire population. It's calculated as follows. The proportion is going to equal the number of items with the characteristic over the number of items examined. Now, if we're talking about an entire population, we're talking about the parameter, so the proportion is going to represent everything for the entire population, and that parameter is denoted by the symbol P. Now, if we're talking about a sample proportion, we're going to use the letter P with sort of the top of a triangle on it, and we call this P hat. For a random sample, we would get different values every time we got a different sample and calculated the sample proportion. The question is, are there patterns to the behavior of the values of the statistic? The sampling distribution of P hat is what we're going to be discussing. So we need to know what the statistics pattern is, or think about a large histogram based on lots or, in theory, all possible values of the statistic. We're going to focus on three characteristics. Where is it centered? How spread out are the values? And does it look like a normal distribution? Suppose that 20% of all people in this area have brown hair. That tells me the parameter value P is equal to 0.20. Now suppose a sample of 100 people is taken and 24 of those people have brown hair. So the sample proportion for this first sample would be 24 divided by 100, or 0.24. Now suppose a second sample of 100 people is taken and 19 have brown hair. So P hat sub 2 is going to be 19 divided by 100, or 0.19. Now suppose that we did this for 100,000 different samples. If I make a histogram of the 100,000 different sample proportions, P hat 1, P hat 2, up to the 100,000th P hat, what patterns would I expect to see? First, the center. The mean of all the sample proportions would be written as mu sub P hat. Now think about what mu means. It means the mean or the average. The subscript P hat tells you what you're calculating the mean of. So mu sub P hat just means if you looked at every possible P hat value you could obtain and calculated the average or the mean, that ends up being the same value as the parameter P, which in this case was 0.20. Notice the center is the value of the parameter, which makes sense. Some of the statistics, some of the P hat values will be higher than the parameter value, some will be lower. But on average, we want a good estimator to be centered at that parameter value. What about variability? How spread out would the P hat values be? Well, the different sample proportions can vary based on a little bit of mathematics that we don't really get into. Okay, we don't cover where all these formulas come from necessarily, but what we're going to do is just use the formula that the spread, the standard error or standard deviation of P hat values, sigma sub P hat, can be calculated as the square root of P times 1 minus P over N. Now P is the proportion of the population, so it's the parameter, which has the characteristic. 1 minus P would be the proportion of the population which does not have the characteristic. And you multiply those two numbers together and then divide by the sample size you use to calculate each different sample proportion. Okay, so it's not the 100,000 different P hat values, but rather it's how many values go into a single p-hat calculation. So in our example, that would be the square root of 0.20 times 1 minus 0.20 or 0.80 divided by 100. When you multiply 0.2 times 0.8 and then divide by 100, you get 0.0016, and when you take the square root of that, you get 0.04. Now, in general, these values will not work out as nicely and stop at just 2 digits or 3 digits after the decimal point. If they do not stop, you need to keep at least 6 digits after the decimal point so that we all get the same z-scores and calculated values later on. What about the shape of the sampling distribution of the sample proportion? Well, it's going to be approximately normal whenever your following conditions are true. Number one, you need to take a good simple random sample of categorical data. The number of successes you expect needs to be at least 10. Now n times p is like how many observations you have times the probability of getting what you've called a success, and we want that number, that product, to be at least 10. This is sort of like rolling a die that has numbers 1 through 6 120 times. You expect to get 20 ones, right? Because n was 120. The probability of rolling a 1 on a 6-sided die is 1/6. So 120 times 1/6 would be 20. So we just expect NP to be at least 10. We also expect at least 10 failures. So that would be n times q for short, or n times 1 minus p. And that just means we expect sort of not getting a 1 in the die example. 120 times not the 1/6 for getting a 1, but the 5/6 of everything else, that would be 100 in that example. So we just expect n times p and n times q to be at least 10, and then we're going to assume the sampling distribution is well approximated by a normal curve. Now, if we know that last condition holds, and mainly what we're going to focus on is the n times p and n times 1 minus p, or n times q, being at least 10, those are going to be the main conditions, then we have a normal distribution where we know the mean and we know the standard deviation, so we can create z-scores. So the z-score would be the sample value p hat minus the mean of the distribution mu sub p hat divided by how spread out the values are, sigma sub p hat. Or substituting, we could write z is equal to p hat minus p, because that was the mean, over the square root of p times 1 minus p over n, because that was sigma sub p hat. Let's look at an example. A report claims that 68% of all Americans spent $800 or more on gifts during the last holiday season. A random sample of 250 people in Cincinnati reveals that 180 spent $800 or more for gifts. First, fully describe the sampling distribution of the sample proportion for samples of size 250 people at a time, assuming the report is true. So assume that 68% value is the correct value. Then in part B, we're going to ask, would it be unusual to see the results we observed, the 180 out of 250, if the report is correct that 68% of people spent $800 or more on gifts. So let's start with part A. First, where would the center be? Well, mu sub p hat equals p, which is the rate of what we're looking at, the characteristic, and the population, and that was 68%, so we write that as a decimal as 0.68. Variability, sigma sub p hat, is that square root formula, so we plug in our values. So the square root of 0.68 times 1 minus 0.68 over 250. If we multiply everything underneath the square root out, we get 0.0008704, and then we take the square root of that, and we get about 0.029503. What about the shape? Well, we took a random sample of people and we categorized them as, did they spend at least $800 on gifts or not? So those are our two categories, our success and failure categories. What about N times P? 250 times 0.68 is 170, and that is more than 10. What about N times Q? 250 times 1 minus 0.68, or 0.32, is 80. That also is more than 10. So the conditions are met, so we can say the sampling distribution of the sample proportion looks like a normal curve where the mean is 0.68 and the standard deviation of p-hat values, or the standard error, is 0.029503. Here's a normal distribution graph with a mean of 0.68 and a standard deviation of 0.029503. And it's a sketch, and what they did was rounded the standard deviation off to about 0.03. So you can see the mean is at 0.68 in the middle, and then it steps off by about 0.03 for each indication that's marked on the horizontal axis. Notice also in the right edge is the part that we're going to be interested in based on the 180 out of 250 sample. So the sample proportion is 180 out of 250, which as a decimal is 0.72, and again that is exact, so we don't have to keep 6 digits after the decimal point. There would just be zeros after that. 0.72 is more than 0.68. Okay, so we want to find the chance that any value of p-hat is what we observe, 0.72, or farther away from the mean, which was 0.68. So that's why we wanted the area to the right of 0.72. First, we want to convert 0.72 into a z-score, right? So what do? Take the value, 0.72, subtract the mean, 0.68, divide by the variability measure, 0.029503. You should get 1.36. Now find the probability that z is bigger than 1.36. So remember, we want the area to the right. The table gives us the area to the left, so we have to subtract. 1 minus 0.9131 leaves us with 0.0869. So 0.0869 we now want to sort of interpret as a probability. As a rule, if the probability is less than 0.05 or less than a 5% chance, then the event would be considered unusual and would make us doubt that we had the correct value for the center of the distribution, or the 0.68 in this case. Now here, the 0.0869 is not less than or equal to that 0.05 cutoff, so from a probability standpoint, we would not consider seeing a sample of 180 out of 250 people who spent $800 or more to be unusual if the proportion for the whole population, if that rate really is 0.68, or if 68% of all people spent $800 or more on gifts. So there's not strong evidence to doubt the fact that P equals 0.68. Now, the empirical rule can also be applied when the sampling distribution is well approximated by a normal curve, because remember, a normal would be symmetric and bounded, so we can apply the empirical rule. Now, values within one standard deviation of the mean would be common to observe. That's exactly what you would expect to happen. Values that are between 1 or 2 standard deviations, either above the mean or below the mean, they would provide a little bit of evidence, but it's pretty weak, that the center is not really quite correct as indicated, and that value probably should be pulled the direction that your sample proportion is located. Now, as values move farther away from the mean, then the evidence gets stronger that your sample doesn't support the value you have for the center or the mean. So values between 2 and 3 standard deviations above or below the mean would provide strong evidence that the center is not the value you indicated for the mean, but more likely is pulled whichever way that sample proportion is located. And then values more than 3 standard deviations above or below the mean are going to provide very strong evidence that the center is not correctly defined, but rather is pulled the direction of your sample proportion. So keep in mind as we move through and talk about different topics, especially when we revert back to things that are normal or symmetric, we can apply the empirical rule as well as just calculate probabilities. So in our example, the value of 0.72 was our sample proportion value, and it was 1.36, so a little more than 1 standard deviation above the mean. So this would be in that 1 to 2 standard deviations above the mean range. So it would provide weak evidence that the value of 0.68, what we defined as our center or our mean of the sampling distribution, is not quite the correct value. It's not the true proportion for the whole population, but that the true value might be larger, right? And larger because 0.72 is larger than 0.68. The probability of 0.0869 also can be considered weak evidence that the true proportion is different than the 0.68 value. The 0.05 cutoff is more common when you're talking about probability and probably corresponds more to strong evidence. If the probability is a lot smaller, maybe less than 0.01, then you might consider it very strong evidence, similar to being more than 3 standard deviations away from the mean when using the empirical rule. So hopefully that gives you a good example of how to not only find the center, spread, and shape of the distribution, but also talk about probability of getting samples and how you can relate either that probability or the empirical rule and determine whether you believe the value you were told was the proportion.